Okay, so now we're what, 5 minutes late? Who cares? All right, so today we're going to go over the coding for the second lab. There's only 4 of you that have submitted your lab report for the first lab, so people struggling with that or what? Or just waiting?
It takes a really long time. It took me like 7 hours.
Yeah, it is pretty long, but that's why I try to go over a lot of the coding with you guys, so we can at least save time there.
Coding was one of the hardest parts.
Yeah.
I don't think the coding was bad because you were pretty thorough with like going over it. It was just like figuring out everything else.
Like what?
Like the like analytical part was a little weird, and then typing the whole analytical part took a while, but
Yeah. Yeah, that's um yeah, so I do prefer it to be typed, but again, for the first lab I said it was okay if you scanned it, but I know typing in Word kind of sucks for math equations.
yeah, I had already typed it when you said it was okay, so I was like,
Yeah.
whatever.
Okay. All right. So yeah, if you have any questions, we'll talk about it after today's lecture. If anyone has any more questions, but specific to you. But if there's any general questions on lab one, then you can ask now. Okay, I'm gonna assume that means no. Okay, Alan, you have a question?
Mentioned that so like if I wrote it down like on my iPad, the calculations, I could just post that as a figure, basically.
Yeah, yeah, you can do that.
Thank you.
Okay. So I uploaded data for the for the second lab on Canvas, so you should download that if you haven't already, because we're gonna need that today for the coding. Okay, so it's under on the homepage. It's under weeks 5 and 6, and then it's up top here for lab data. All right, so we're gonna need that once we start using MATLAB today. Got to have it in the same folder that we have the MATLAB code in. All right, so I'm gonna give you guys, I don't know, maybe a minute or two to download that, and then we're gonna start with the coding.
What are we downloading?
Download the lab data for today.
We're just gonna be importing from the Excel doc.
Yeah. It's not sharing my screen, right? That's great.
Are you on like Linux or something? Some like different operating system? It looks different.
Yeah, I'm using Linux.
Oh, okay.
It's Zoom is usually okay with it, but now it's not great today. I know they had an issue too, just Zoom in general with sharing an iPad screen. So that might have been why I had an issue last time, but I don't know if that's fixed or not now. Okay, I think we're good now. All right, does everyone have it downloaded?
I got it.
It seems really laggy sharing the screen, or maybe it's just on my computer. I know it does that sometimes. I don't know why. For my, again, I have my PC setup, and then I have my laptop to the side, and I'm looking at that. Okay, am I scrolling on your screen right now?
Yeah, it doesn't seem too laggy.
Okay, cool. All right, so I'm just gonna have a little review here for Lab 2. So again, we're not doing this experiment in person. We usually would. So let's just go over what we would have done. So we'd go down to the lab, and we would have a beam, and on this beam there would be a weight. I actually have some pictures from my lab report when I made it. You guys can see it, right?
Yeah.
Yeah.
Okay. I don't know. It's really weird because on my laptop, it was like, it just started showing these pictures. So kind of weird. All right. So in your lab report, you shouldn't, well, you don't even need to include pictures since we didn't do the lab. But if you have a picture, you should do a better job than I did here. Your picture should be centered on the page, and then the caption should be centered under the picture. Anyways, this is how the lab was set up. So we have this setup here. We have a beam. There's a motor that's behind this little circle here. And we would increase the RPM of the motor, and then it would start to induce vibrations on this beam. And we would increase the RPM of the motor until resonance was achieved on the beam. So there's this cable here for lab view where we would read the resonant frequency. So that would be read in hertz in lab view. And then this little paper disc here that would spin around, and you see there's a little circle cut out. We would use a strobe gun right here, and then we'd read the RPM reading with the strobe gun. And then we would convert both lab view and the strobe gun readings to radians per second. So here's a better view of the motor, so you can see that there. And also you can see in this picture here, figure 5, we've added weight to the beam. So you see we have these 3 kind of discs here, while up here, there is nothing added yet. So we would start out with a weight or an added weight of 0. So it'd just be the beam here. We would increase the motor until we had resonant frequency. Then we would, put down those readings on a piece of paper. And then we would add, I think it goes by 4-pound interval. So we would put 4 pounds of external weight on this beam here, just on this little shaft right there. And we would then increase the RPM of the motor, get resonant frequency again, and then we'd keep doing that for added weights up to, I think, 16 pounds. So that's the general gist of this lab. And then we would, go over the theory that we did last time, and we would have to find stuff like the theoretical natural frequency for this setup, so we had a few calculations for that, for the theoretical portion. So one of them was calculating the theoretical natural frequency for a simply supported beam like we have here. And the other one was calculating the natural frequency for this entire system. So that's including the weight of the motor and the added weight of the system. And another few calculations, we would calculate the effective stiffness of this beam, the effective mass, and then we're going to compare that to our theoretical calculations for those as well. Okay, any questions on that? Okay. All right, so I'm gonna pull up MATLAB and I'm gonna keep our handout open just so we can kind of reference that a bit. Okay, so make sure you have MATLAB opened up, and then we're gonna start doing the coding. It's not too much. I forget how much we had last time, how many lines. I think last time was more.
Yeah, I have like 134 lines from last time.
Okay, yeah, I have 141, but depends how you have it organized. Actually, really, 136. So it's actually kind of similar, to be honest, but it's not too bad. Okay, so I'm going to make a new script here. Okay, so make sure you're making a script because that's what we need. So you're going to go in the top left here, click on new, and then new script. Or you can do Control N. Jeez, my laptop is so loud right now. I have MATLAB opened up on my laptop and Zoom, so the fans are just blowing extremely hard. Okay. Yeah.
Sorry, do we have a MATLAB code for this yet, or are we just looking at the Excel sheet?
Just the Excel sheet. We're going to make the code right now as a class.
Okay, thanks.
Mm-hmm. Okay, so if there's a question in the chat, I don't get any sound notifications. I think I need to configure that, but right now I can only see MATLAB on both of my computers. So if there's a question in the chat, someone yell at me.
Yeah, we'll stop you.
Okay, thank you. All right, so let's get started. Or if you have a question, just use your mic too if you want. Okay, so yeah, I'm gonna keep looking over to the left here for my laptop because I have the script open there. So let's start off with the comment here, EGME 476A. This is lab 2, fundamental natural frequency of a beam, if I can type. All right. So we're gonna clear the memory. So again, if you're not as strong in MATLAB as, you know, you wish or something, I don't know. The comments here in parentheses or a percent sign, that's a comment in MATLAB. So MATLAB isn't going to try to run that line. And we're always going to start out by clearing the memory. So we can clear any variables that we don't need. And then we can clear the text in the command window. All right. Okay. It's kind of annoying me that I can't see the chat, but whatever. All right, so the first thing we're going to do is define our knowns. I guess before that, I'll show you the Excel sheet that we have. So all I did there is I went in the current folder and got to make sure that the Excel sheet is in the same folder that you're working in for the MATLAB script. And if you go over here and you just double click on beam_data.xlsx, then it's going to open up this kind of import wizard in MATLAB, and we can look at the file. Okay, so here's what we have. We have 3 rows. We have the added mass that we have for the system. And then we have lab view reading. So this is the reading for the resonant frequency that lab view recorded. Again, that's in hertz right now. Did I specify that? I should have. Yeah. Then we have the strobe gun frequency that was recorded in RPM. And then you see I have for each corresponding added mass for the system or added weight, I have T1 and T2. So that just means trial 1 and trial 2. We took 2 readings for each added mass for LabVIEW and for the strobe gun. So for a mass of or an added weight of 0 pounds, we had 2 readings for LabVIEW and then 2 readings for the strobe gun. At 4 pounds, 2 readings for LabVIEW, 2 readings for the strobe gun, and we keep going like that. All right, so I'm going to close out of this import wizard because we're going to import this using code instead. So before we do that, though, we're going to define some knowns that we have in the system. All right, so we have the mass of the beam. So for these, I didn't like put in an Excel sheet or anything like that. I just took it from a past lab. So I took it, I think the data that I have is from Dr. Park like 2 years ago or something. So it looked like everything seems good for the accuracy. You'll see later on that when we compare I think it was the effective mass, there was a lot of error. So I don't know if someone recorded the mass wrong in the lab or what, but when I took this lab as well, there was a lot of error for that part too, but we'll see later on. Everything else is pretty good though. All right, so we have the mass of the beam. That's going to be 0.1445 divided by 12. So what we had is slugs. That's 0.1445. And then we're dividing by 12 just to get our units consistent for what we're going to have later on. So the base units for slugs, I think it's pound-force times second squared divided by feet. And then we're just going to convert that to pound-force times second squared divided by inches. So kind of a weird unit here, but we're just doing that to be consistent later on. Okay, so I'm always going to specify in a comment what our units are. Okay. I should also first say mass of beam. Okay. Then we're going to have the mass of the motor at 0.3977 divided by 12. Again, we're kind of having those weird units here. So pound-force, second squared divided by inches. Let's do that. Okay, and then we have the length of the beam. That's 32 inches. Okay, the height of the beam. I know this stuff is kind of tedious right now. Height of the beam is 0.5 inches. The base of the beam, or kind of the thickness of the beam, is 0.5. Okay, the base of the beam is 1 inch. All right, the elastic modulus of our beam is 30 times e to the 6 psi. So 30e6. And again, since we have psi, we're sticking consistent with our units of having inches. And then the moment of inertia. So I'm putting it here for knowns, but we're really doing a calculation right now. So that's base times height cubed divided by 12, right? Yeah. And I had that in the slides as well. So if you want to reference that. So we have the base of the beam times the height of the beam cubed divided by 12. And that's because we have a rectangular beam. All right, just making sure I typed it all correctly. And that's the moment of inertia for the beam. And our units for here are inches to the 4th. All right, then I'm also going to just define a row vector here for the added mass of this system. We could import that from the table, but why do that when I can just make a row vector? So it's going to be 0 for an added mass of 0 pounds, 4, 8, 12, 16. And then we're going to divide that by 32 times 12. And again, that's to convert our units here. So we first had pound force because it's in weight. Then we need to convert that to mass, and then we're converting our mass into the same units that we've been using for mass. So added mass, that's going to be units of pound. So this up here, sorry, I shouldn't have pound force. That should be pound. It's really a pound mass. So we have pounds per second squared divided by inch. Okay, that's all of the knowns. So everyone done typing that or no? I'm gonna make sure you're all done.
Just need a couple seconds more.
Okay. Adrian, I didn't see your comment before. Yeah, it's a MacBook, my laptop. The fans on that are ridiculous. They get so loud. I have another question for all of you. On the shared screen right now, is there like a huge box where it's kind of grayed out, or is it just in the top right?
On the top.
Yeah.
Okay. In the top right?
You even got like a small one in the middle.
Really? Why? This is so annoying.
I only see it in the top right.
Yeah, I only see it in the top right. It's just a gray box in the top right.
Okay. All right. I'm gonna leave it there because that's the chat box, and Zoom kind of sucks where they don't just have that transparent, they block it out like a box. I don't like Zoom.
It's trash.
Yeah. And like the video quality, they compress it a ton, and then the audio quality that gets compressed, and then there's this issue. Not a fan. All right, does everyone have it all typed out? Okay, I'm gonna assume your silence means yes. All right, so we're gonna import the data now. So again, we're just gonna import our Excel sheet over here. So in past versions of MATLAB, if you've imported data before, you would use read XLS or read CSV, depending on the file type. They kind of deprecated that in 2020 or 2019A, I think. So you can still do that if you want, but we're going to use their new function that's going to be called read table. So what I'm going to do is I'm going to call this file name. Doesn't matter what we call it. This is just our variable that I'm going to assign to what we're importing. Now we're going to do read table. And now we're going to put the file name of what we're going to import. So if you didn't change the file name, it's called beam_data.xlsx. You have to put the file extension on there as well. And then we're going to type, we're going to put a comma, and then in apostrophes, preserve variable names, comma, false. Okay, and that's basically that last argument is going to make it so it's not going to show the or import our variables up here for T1 and T2. Okay, so if we run this right now, it's going to ask us to save the file. So you want to save it in the same directory that we're currently in. When you save your file, you have to start it out with a letter right away. And it also can't be the name of a function in MATLAB. I doubt anyone's going to do that. Just call it, for me, I'm going to call it class beam. I don't know. It doesn't matter what you call it. Class beam nat frequency. Okay, so now that we saved that, it's going to run at the same time because how I did it is I tried running it and then I had to save it. So in the workspace on the right, we have all of our variables that we just defined. So we have the base, the beam, elastic modulus, whatever, all of that. And we also have a file name here. So you see if I scroll over, it says it's a 3x11 table.
Professor?
Yeah.
I'm sorry. The chat window's there, so we can't see the workspace. Is there any way to move that?
Okay, yeah, I'll close out of it. It's kind of weird because I think for some of you, you can see it. Can you see it now?
Yeah, thank you.
Okay. Okay, so yeah, if there's just a comment in the chat, let me know. Okay, so we have file name. If I go over that in the workspace, it shows that it's a 3x11 table. If I double click on that, then we can see what we just imported. So again, it's not importing what we had up here. We can see it in the table, but it's not importing T1 and T2. All right, so we have our mass, we have the lab view reading and the strobe gun reading, and then we have all of our trials here.
Professor?
Yeah.
Mine's saying that I have invalid parameter name for preserve variable names.
Okay, did you typed it correctly, right?
Yeah.
It should work. Or let's see, what
getting
version are you on? Are you on 2020A?
No, I'm on 2019A.
Okay,
On
I'm pretty sure.
2020B.
Okay, well, 2020B should be fine. I guess, well, you do need to have this though. And I can't look at your screen. I don't know, just read over it again, because 2019, they started using this feature then. Just you're 100% sure you typed it all correctly, right?
That one line of code?
Yeah. I know it's like such a simple thing, but.
Mine's not working either.
Okay. Well, it's bad. Is it not working for everyone?
It worked fine for mine.
Okay.
Yeah, it works fine for mine too.
Mine's typed correctly, by the way.
Put it in the chat if you want to copy paste it. It might, I don't know, you might be reading over something.
Yeah, I'll do that. I'm gonna stop sharing my screen really quick. Okay, I'm gonna put it in the chat and you can try it. Or Tyler already put it in there. Okay. Adrian, you wanna share your screen if you're fine with that? Just so I can read it over too.
Sure.
Okay. Okay, and you have the data imported in the same folder, right? I can't see it right now.
Should be, yeah.
Okay, it should work. Obviously, it's not. Okay, so I don't know. For you then, I'll have to help you after class. How many people is this not working for? I know there's at least 2 of you.
I typed in, or I copied and pasted Tyler's code and mine's working now. So I must have just typed something wrong.
Okay.
Yeah, I commented out my first one and then I just copy and pasted Tyler's, but it's still doing the same thing.
Okay, so Adrian, I don't know, it kind of sucks for now, but stay after class and then I'll help you out then.
Okay. All right, I'll just follow along then.
Okay. All right, so let's continue. Hopefully most of you, it works, because it should work after 2019A. That's when they started implementing this. Or if I can remember the exact code, tried read XLS. Is that the command, or is it read XLSX? Hold on, I'm going to pull up my slides for 205 because I have the command there. Where was it? Arrays. It's XLS read. Okay, XLS read. And then you could type in the file name, so being data.xlsx. Let's see what rows they import though. Okay, so if you do XLS read, it's going to import it. You see it didn't import our rows here. That's okay, because we're actually going to take that out in a second here. So for those where it didn't work using read table, try XLS read. It's kind of deprecated, but it does work still, so you can do that. But note that it's a 3x10 double, so it's not a table, it's an array. But that's fine because we're going to convert our table in a second too. Okay, so we have the data imported, and before we convert to the table, we're going to initialize our arrays because we're going to be using for loops today. And when you use a for loop, you should pre-allocate all of the variables that you're going to calculate in an array of zeros. We do that to just save memory and to make our code more efficient. So our stuff is, pretty small. We wouldn't have to do it, but it's just good practice. Okay, initialize arrays. So I'm going to do, we got a few here because this is going to be basically everything that we calculate today. Right, I'm going to comment this one out, but again, if you kind of do the function for read table, then do this line right here. Okay, so theo underscore nf, that's going to be our theoretical natural frequency. And then we're going to do zeros, 1, 5. This is going to be a row vector that we have in the end. That just means have a row vector of zeros. We have one row and 5 columns. And this will be the natural frequency of the system with the added mass. And it's, let's change this to theo. Okay, this is our theoretical natural frequency of the system with our added mass. If I run the code right now, and I look at that array, you see that it's just one row with 5 columns, and it's all zeros right now. Okay, and then we're going to do experimental natural frequency. You can call these whatever you want, but you got to be consistent later on. So this is experimental natural frequency trial 1. And I'm going to call this zeros, 3, 5. Yeah, so here we have 3 rows. Hold on, I'm going to look at my code. I changed it a few times last night. Okay, yeah, it's fine. Okay, so we're going to do experimental natural frequency trial 1, and we have 3 rows here and 5 columns. So, oh, I put zeros 2 times. Okay, so we have 3 rows and 5 columns. Maybe I should have done this a little different yesterday, but this is getting the 3 rows that we have in file name, and then it's going to have 5 columns because we should have 5 columns that corresponds to trial 1. So I'm just going to keep it like I have it, but yeah, maybe I should have done 2 rows. So trial 1 values, and then we're going to have experimental natural frequency, trial 2, zeros, 3, 5. This will be for trial 2 values. Then experimental natural frequency, average. So here, this is just a placeholder for when we calculate the average natural frequency before or for our 2 trials. And zeros, 3, 5. Average nat frequency values for trials. All right, experimental. LV, that just stands for lab view. So experimental LV, NF, experimental lab view, natural frequency. This will be zeros of 1, 5. So in this case, now I'm just going to assign an array here where it's again a row vector that's 1 by 5. This will be what we have for one of our results in the end. So we're going to have results for the lab view, natural frequency, and because we added weight 5 times, or we have 5 kind of intervals of added weight to the system, we should have a row vector of 5 columns. All right, so lab view, natural frequency, then experimental STR, that's gonna stand for a strobe gun. 0 is 1 comma 5. Strobe gun, natural frequency. Experimental LV, we're almost done here. LVNFPE. This stands for experimental lab view natural frequency percent error. So we're going to calculate the percent error that we have compared to the theoretical values that we calculated up top here. So zeros and then 1 comma 5 once again. Lab view natural frequency percent error. One more experimental strobe gun natural frequency percent error. 0 is 1 comma 5. Strobe gun natural frequency percent error. All right, I know that was a lot, so I'll give you a minute to type all that out. And I'm just going to clean this up so it looks a bit better. I don't know if MATLAB has a way to align this on the equal signs. If I use MATLAB in a text editor, I can do it really easily, but whatever. All right, so I'll give you a minute to type all that out. Sorry, I didn't realize my chat was opened up again. All right, once you guys are done, you know what? I'm going to make a poll here so I can more easily see when you're done. I'm trying not to block the code. Of course, as long as this is taking me, you guys will be done. Yeah, okay. I'm actually going to go on my iPad really quick, and I'm going to pull up the code on my iPad so I can look at the chat on my laptop. And then my laptop doesn't have to be so loud. Okay. It doesn't like it, even though it's a .m file. I thought it could maybe still show the text, but I guess not. Okay, let's move on now. 16 of you have answered, even though there's 21 in here. I guess we lost some people. How sad. Let me go to MATLAB again. All right, so now we're going to assemble our arrays into, or assemble the data that we have. So we're going to take our table that we have and make that into an array right now. So assemble data into arrays. Okay, so I'm going to have a new variable here called A, and then I'm going to assign our converted table to an array. So we're going to do table to array, that's our function. Then I'm going to specify file name, because that's what we called our table up here, comma. Now I'm going to specify all of the rows that we have. And then we're going to go starting the second column to the last column. Okay. What did I do wrong? File name. I shouldn't have had a comma there. There we go. All right, so if I look at A right now, now it's a 3x10 double. So for those of you that used XLS read, that was a 3x10 double. So you already had that. If you used read table up here, then we had to convert it into an array. And using all of the columns and, all of the rows and then columns 2 to the last column, and we get a 3x10 double where we have these values here. All right, now we're going to assign each trial into its own array. Okay, so now we're going to really start actually doing stuff. I know there was like a lot of kind of prep work. Okay, so now we're going to use a for loop so we can save some typing for ourselves. We don't want to type out like 200 lines of code. So for I equals 1 to 5, we have 1 to 5 because we have 5 trials for our, well, we have 5 values for each trial. So we had 10 trials in total, but for trial 1, we're gonna have 5 values in the end. So you'll see. Okay, so we have 5 values for trial 1 and 5 values for trial 2. Okay, so we're going to do experimental natural frequency, T1. So you see up here, we already allocated some an array for this. Okay, and then for this, I'm going to do all of the rows, comma, I equals to A, all of the rows, I times 2. I'll talk about this code. So first I'm going to type it all out and then we'll talk about it. Okay. So I'll talk about it now. I'm sure you guys are still typing now. Maybe, I don't know. So we're using a for loop here from 1 to 5. We want to separate our trials into their own array. So we have trial 1 and trial 2. So each of those should have 5 corresponding values and, or I should say 5 corresponding columns. And then we have values for the strobe gun and for lab view. So if I run this code first, and yep. Okay, so what we have here, let's talk about the code. So we have experimental NFT1. So this is our experimental natural frequency for trial 1. I'm going to open up our worksheet right here. You know what? I'm going to change the layout.
Quick question. Did you say if we're using XLS read, we can just comment out the table array?
Yeah, you shouldn't have to do this line here. You should already have in that format.
Okay, thanks.
Mm-hmm. No, that's not how I wanted it. Okay, so let me open up A here. Let me go back to the default. Okay, so we have A. Now I want to get all the values for trial 1. So first what I have to do, I want all of these rows. So that's why I have the colon right here. That's going to say all of the rows. That's also why I have this allocated right here. So this is saying to take all of the rows, and then for the column, look at our counter here, which is I. So that's going to go from 1 to 5. So I should have 3 rows, because I said take all of them, and I should have 5 columns. So our output should be a 3 by 5, which if we click on it, we can see over here, it's a 3 by 5 double. And we're looking in our matrix A, which we just converted earlier on. That was from the table to array. So that's this line right here. Okay, so I'm saying for trial 1, what do we have to do? We have to look in this matrix A. We have to get all of the rows, and then I have to specify which columns I want to import. Because again, I want this for trial 1. So I'm doing I times 2 minus 1. So if let's pretend we're going for the first value right now. So we have I equals 1. So we have 1 times 2 is 2. Minus 1 is 1. So we're starting in the first column for A. So we're going to get all of these values right here. And then it's saying now let's go to 2. So then 2 times 2 is 4 minus 1 is 3. So the next value or the next column that we're going to assign to that array is column 3 in this matrix A. And then for trial 2, it's the same, but instead we're doing I times 2. So if we start out for the counter of 1, we have 1 times 2. That's 2. So we're just going to import column 2. And then let's say we're at the second counter. So I equals 2. 2 times 2 is 4. So we're going to import that fourth column. All right, I know that's a lot of stuff. So maybe you have to kind of break it down on your own after class if you are like a little overwhelmed here. Maybe you're not, I don't know. But this is just allowing us to import only the columns that we want to import. So I'm only importing all of the respective columns for the first trial for each added weight in one array. And then the other array, I'm only importing all of the columns for the second trial for each added weight. All right, so we've done that. And now we're going to do our calculation. So yay, finally, theoretical calcs. So I'm kind of going in depth here just for those of you that maybe aren't as confident in MATLAB as you'd like, then hopefully this kind of breakdown helps you understand it. If you want to talk to me after class in more detail, we could do that too.
What is that little percent? It like highlights everything. What is it doing there? Is
Oh
it
yeah,
just
so
like
that's just
sectionalizing?
Yeah, just making a section, yeah.
Okay.
Okay, so theoretical calcs. We'll do Theo and FB. So we already allocated this. Actually, no, we didn't. This will only be one value, so we didn't have to allocate an empty array before. So Theo and FB, that's going to be our theoretical natural frequency for the beam, for a simply supported beam. So let's quickly go over here. Oh, yeah, I'm right. So, so that's going to be this equation here. I think you can see my screen, right?
Yeah.
All right. Okay, so we're just using this equation right here, equation 6. So let's go back to MATLAB, and we're just going to type that out in MATLAB. So we have pi squared times the square root. So for the square root in MATLAB, we just type sqrt, parentheses, e underscore beam. That's our elastic modulus, times I underscore beam. So I underscore beam, that's our moment of inertia, divided by m underscore beam times L underscore beam to the third. And then we're going to close all of that out. So you see for my parentheses, I kind of add in all these spaces here just to make it easier to read. You don't have to do that though. And again, this is the natural frequency for a simply supported beam. All right, and let's quickly go back here. So again, that's just this equation right here. We have pi squared times the square root of our elastic modulus times the moment of inertia divided by the mass of the beam. The mass of the beam that was given to us, we already know that. And then the length of the beam cubed. And then if we run our code, so to run your code, if you don't want to go, up to the editor and press run, you could just press F5. So Theo NFB, our theoretical natural frequency for a simply supported beam is 277 rads per second. I should have put in the units there, but whatever. Right? Theo underscore KE. So this is going to be the theoretical effective stiffness for the beam. And again, we have an equation for this as well in the slides. So let's show you that really quick. I think I had that in the beginning. Yeah, right here. So on slide 8, we have the effective stiffness of our beam is going to be 48 times the elastic modulus times the moment of inertia divided by the length cubed. And then our effective mass is 0.4857 times the mass of the beam. So simple enough. So 48 times the elastic modulus of the beam times the moment of inertia of the beam divided by the length of the beam. What was it? Cubed? Yeah, cubed. And then we have the Theo equivalent stiffness. And then we're going to do Theo underscore ME for the theoretical effective mass. 0.4857 times the mass of the beam. And so, earlier on, that's why we did all of our unit conversions in the beginning, so we don't have to have them all kind of scrambled throughout the code later on. All right, if you run the code, it works fine. So our theoretical stiffness is 457. Yeah, I didn't put the units there. I think it's pounds per inch, if I remember right. And then the effective mass is going to be, where is it? DOME 0.0058. So if I remember right, this is when we're going to have that huge percent error for the theoretical versus the experimental part, but it's only for the effective mass. Okay, so do we have any questions so far on any of the coding or, anything?
Yeah, this is kind of a trivial one, but on line 42 over on the comment, does it just say theoretical natural frequency for? Okay, gotcha. Simply supported beam. Thank you.
Yeah.
I did the XLS read, but if I comment out the defining the A to be a table array, if I comment that out, it says that it's an undefined variable.
Oh, okay, yeah, that's because you're using A later on. So when you did XLS read, put A up here. So define, the variable A on the left-hand side.
Instead of file name?
Yeah.
Okay.
And then that should work now. All right, any other questions? Okay. All right, so now we're going to define the natural frequency for the entire system, or we're going to calculate it. So this compared to our simply supported beam, for the entire system, that means when we add the weight throughout. And we added weight 5 times, so we're going to have an output of 5 values. All right, so natural frequency for entire system. And we're going to use another for loop here. So 1. Here, I'm going to do length of m. So I could just put 5, but when we do something like the length of m, oops, this should be 1 to the length of m. So when we do something like this, it's more convenient for us if we were to have changed this row vector up here at some point in time, if we added another weight at some point in the experiment, all we have to do is change this part here, and then we don't have to change any other code later on because I have this specified as 1 to the length of m. If I go in the command window, the length of m, that's 5. That means we have 5 values in that row vector. So you can put 1 to 5, or you can put 1 to the length of m, but length of m, again, that's more convenient or efficient. All right, so Theo nf of I, and again, we're doing Theo nf of I because we want to go through for all 5 values, equals the square root of Theo underscore ke divided by, in parentheses, go away, Theo me plus m underscore motor plus m's of I. And then we're going to end that. So that's going to be our theoretical natural frequency for the entire system. I'm going to change the page really quick. Let's see, where was that? The theoretical natural frequency for the entire system. Maybe I should have wrote this down before. Okay, so really that's just the square root of k divided by m, but m in this case is going to be our theoretical mass, or effective mass, plus the mass of the motor, plus our added mass. So I don't think I have that actually written out in the slides, but that's essentially what it is. The square root of our theoretical effective stiffness here, divided by m. So m is going to be, in this case, the theoretical effective mass plus the mass of the motor plus the mass for each added weight. If I run this and then I go to Theo underscore nf, then we see that we have 5 values here. So we have all of the values for each added mass. Okay, we got one more thing we're going to do here for the theoretical calcs. We're going to separate, or actually no, not for the theoretical calcs, for the experimental calculations now. So what we're going to do now is separate and calculate the experimental results. So when I say separate, we're going to separate what we have for LabVIEW and what we have for the strobe gun. So we're going to do another for loop. I could have put a lot of this stuff in the same for loop, but, to be more efficient, but I have them in different for loops just to kind of separate the code in a more easy to read way. So we have for I equals 1 to the length of m. Again, that'll just be because we want 5 values or 5 columns. And then experimental underscore LV NF. So we allocated this before. Experimental LVNF, that was zeros of 1, 5. So that's going to be 1 row and 5 columns. So we're going to iterate that for the counter I equals experimental natural frequency average. So we calculated this before right here. Or maybe not calculate, but we assigned this variable before. So this is the experimental natural frequency, the average that we have for each respective trial. So if we look at this here, that's a 3 by 5. So we have all of our, we have trial 1 and then trial 2 for each added weight. Or really, sorry, the average of those trials for each added weight. Okay, so this time I'm going to do 2, I. So here, let's go back to this really quick. So I'm typing 2, I because I want the second row. So really in my code, I shouldn't have even imported this, this top part, but whatever, it doesn't really matter. But because I want to look at the LabVIEW readings, that's this second row right here. So that's why we have a 2. That means row 2. And then comma I means the rows from I equals 1 to 5. All right, so 2 comma I times 2 times pi. So 2 times pi, we're just converting hertz to radians per second. So all we're doing is taking our values from our average natural frequency that LabVIEW recorded for each added weight, and we're converting that to radians per second. Okay, and let's put a comment. Average LabVIEW nat frequency. All right, next one, experimental. LV, NF, PE. So now we're going to calculate our experimental error that we have to the theoretical value. Okay, so for this, that's the absolute value of our experimental value minus the theoretical value divided by the theoretical value times 100. Simple formula, I'm sure all of you are familiar with that. Okay, so we have the absolute value, so we type ABS, experimental LabVIEW, natural frequency of I, we want to have all 5 values, minus theo underscore NF I, we want to have all 5 values. We need another parentheses here. Divided by theo underscore NF and then I once again, and we're going to close all of that out. There we go. So we have the LabVIEW nat frequency percent error. Okay. So what I'll do right now is I'll type an end. We're going to add some more, but if I run this right now, oops, I typed EXP wrong. So EXP. So if we look at that percent error, we have a row vector that's 1 by 5. And this is our, oh, I didn't multiply by 100, did I? Yeah. Okay, multiplied by 100 because we want to have percent. So our percent error for LabVIEW, for the natural frequency that LabVIEW recorded for each added weight. So we have 1.27% for an added weight of 0 pounds, 0.8458% for an added weight of 4 pounds, and then so on and so on, okay? And again, we have 5 values. All right, is everyone following along? I feel like I don't know. I think it's a lot if you're not familiar with MATLAB, but hopefully it's okay. But I want some feedback.
Yeah, I'm still following along.
Okay, good. All right, next one we're going to do is the experimental strobe gun natural frequency. So again, we have to iterate on I. So we have our 5 values. And then we have EXP underscore natural frequency, average. Now we're going to get the third row. Okay, so we're going in the third row because we're looking at this matrix right here. The third row corresponds to the strobe gun reading for the natural frequency. Right now, this is in RPM, so we have to convert that. Okay, and then we have times 2 times pi divided by 60. So this is taking our RPM to radians per second. Okay, average strobe gun natural frequency. All right, and now we have one more to type in here, which is the percent error. So we have the absolute value of our experimental strobe gun natural frequency, iterate on I, minus theo NFI divided by theo NFI multiplied by 100. This is our strobe gun Strobe gun, natural frequency. Gee, I cannot type %error. All right, if we run it. So I'll go back to the code really quick, but we have our experimental strobe gun natural frequency %error is 0.84% for an added weight of 0 pounds, 1% for an added weight of 4 pounds, 1.88 for an added weight of 8 pounds, and so on. So our %error for both LabVIEW and the strobe gun, they're pretty good. Oh, I think they're really good. All right. Okay, so now let's see what we have to do. We have just a few more calculations here. So one of the other things that we have to calculate in the lab is the effective mass and the effective stiffness experimentally. So for that, that's when we have to make this plot here. And then from that plot, we can find the, let's make that bigger. So from our plot here, we can find the effective stiffness experimentally by looking at the slope and taking the reciprocal. And then we can find the effective mass by finding this x-intercept value right here. All right, so let's go ahead and do it. So the first one we're going to do is for LabVIEW. So I'm going to do LabVIEW. Yeah, let's do LabVIEW Calcs, whatever. All right, so what do we have to do? We have to use, well, first we're going to fit our data. So basically what we have here is we have mass, the added mass of our system. So we have our x-axis, and our y-axis is going to be the reciprocal of the natural frequency squared that our LabVIEW software recorded. Okay, so what I'm going to do is type LV slope. I'm basically going to calculate the slope right now for that plot that we just saw. So we only have 5 data points. So what I'm going to do, and this is part of the experiment as well, is we have to do a least squared fit for those data points. So we're going to get a linear line right now to find the slope. So I'm going to call it LV slope just for LabVIEW slope. Then we have to use the Polyfit command. So that's going to do a data fit for our polynomial that we have. So we have 3 arguments that we can specify. The x data, which will be our added mass. The y data, which will be the reciprocal of the natural frequency squared. And then n, that's going to be what kind of degree we want. So we're going to put 1 because we want a linear degree or a linear slope. So we have polyfit m. Again, that's a row vector for the added mass in the system. And comma 1 divided by exp lv nf. That's our experimental natural frequency for LabVIEW. And then we have to do squared. So you'll see I put a dot and then the squared. That's because we have a row vector for this experimental natural frequency. It's a 1 by 5, and because we're squaring that, we have to do this element by element, if you remember that from MATLAB. So if you didn't have the dot, you'd get an error. So just make sure you have the dot right before you square it. Oh yeah, and then I need a comma 1 because I want it to be linear. Okay, and then we're going to suppress it. And then we'll add a comment just so we know what we're doing here. Fit slope using polyfit. If I run this now and I look at LV underscore slope, we have a 1 by 2 double. This just stands for y equals mx plus b. So we have our slope right here. This is 0.0022. And then b is right here. So we have 8.688 times 10 to the minus 5. All right, I think it's like a lot of MATLAB review here. So yeah, hopefully you remember all this stuff. At least a little bit. Okay, so now we have to find our experimental value for the effective stiffness. So we just have our formula. That's the reciprocal of our slope. So experimental effective stiffness for lab view. That's 1 divided by LV slope. And I'm going to specify 1. So putting this 1 right here, that means to take the first value in our row vector here that we just found for LV slope. So specifying 1, that means to specify our slope here. Because again, y equals mx plus b, we're specifying the slope. Okay, there we go. Let's add a comment. Experimental equivalent stiffness. Okay, and we'll do experimental effective mass for lab view. Okay, so that's going to be the x-intercept. So for this, we're doing the experimental effective stiffness for lab view is equal to LV slope. This time, the second value, so our intercept, divided by LV slope 1. Okay, and that's going to be our x-intercept right there. So if you did, if you like wrote out y equals mx plus b and you wanted to find your x-intercept, this would be how you would find it if you like did some algebra and solved for x. Okay, so we have that. Again, that's just our y-intercept divided by the slope. Okay, and that's our experimental equivalent mass. Okay, let's find the percent error for these now. Experimental effective stiffness for lab view, and then the percent error, absolute value of experimental stiffness for lab view, minus the theoretical effective stiffness, divided by the theoretical effective stiffness, multiplied by 100 to get a percent. Add a comment, percent error. Effective stiffness percent error. Effective stiffness. Okay, and then we have the percent error for the effective mass for lab view. So much stuff. EXP, that should be EXP. ME, LV, so our experimental effective mass for lab view minus the theoretical effective mass divided by the theoretical effective mass times 100. Effective mass percent error. There we go. Run it. What do we have? Effective stiffness for lab view percent error is 1.12%. The effective mass for lab view, that percent error, what? 587%. Yeah, what? That's right though. Well, it's not right. Someone made a mistake somewhere, and or maybe there's some theoretical discrepancy here, but yeah, that's what we have. So there is some issue there, whether that was a data recording or whatnot. So, you can discuss that. You should discuss that in the report, but I didn't type any code wrong here. At least I don't think I did. That's literally what it is. All right. Anyone still there? I feel like I'm talking to myself.
Yeah, well, we're still here.
Yeah, I'm still here.
Okay.
Just typing away.
Yeah. Actually, we're not going to do the plot quite yet. Let's do our strobe gun calculation. So we have to do the strobe gun calculations, and then we can do the plots. Okay, so for this, we're going to do the same kind of thing that we just did for lab view. So we're going to use Polyfit once again so we can fit a line to our 5 data points that we have. All right, so we're going to do str slope, so strobe gun slope equals polyfit m. That's going to be our x data, and then 1 divided by. Oh yeah, and then I have a dot right here too for divided by, because we're dividing by a row vector. Experimental strobe gun natural frequency squared, and then 1. So the comma 1 again, that's to specify a linear degree, so a degree of 1. And then we'll add a comment. So fit slope using polyfit. So if I run this now, then str slope, we have our two values. So we have y equals m, that's right here. So the slope is the same, at least for this degree of accuracy. And then our y-intercept right there. Where's LV slope? So you see that our y-intercept, that's a bit different between the two. Let's close out all this stuff too. Okay. EXP. So now we're going to look at the experimental effective stiffness for the strobe gun. So 1 divided by str slope. And then again, we want the first value. Yeah, to get the effective stiffness right here for the strobe gun. So if I run this, exp ke str 452, and then so we do have a difference here. So the slope is different. MATLAB just for their significant figures that they had, they didn't show enough digits, to show the difference. Because again, where are we at? There's so many variables here. What did I call the slope? STR slope here. So you see we have a 0.0022 for the slope. Really, there is more numbers here, but for how our formatting is right now for the significant digits, doesn't show the difference. But our effective stiffness for LabVIEW and for the strobe gun, they are different. They're very similar, but they're a little different. All right, so that's our experimental equivalent stiffness LabVIEW, or sorry, strobe gun. All right, and now we're going to do the percent error. So exp ke strobe gun percent error absolute value. The experimental stiffness for the strobe gun minus the theoretical stiffness. Yeah, I could copy and paste. Divided by the theoretical stiffness times 100. Effective stiffness percent error. Exp ke str, or sorry, ME. I'm like going through the motions right now. Absolute value. Experimental effective mass for the strobe gun minus the theoretical effective mass divided by the theoretical effective mass times 100. And effective mass percent error. I spelled effective wrong here. Effective. All right, let's run it. Okay, line 72. I don't have a experimental ME STR. Where was I calculating that before? Experimental. Oh, I didn't calculate it. That's why I skipped the line. Experimental ME STR. That's going to be our x-intercept. So we have to do str underscore slope 2 divided by str slope 1. So maybe I'm calculating this part wrong here. I don't think I am though. You guys could double check me. So our effective stiffness, strobe gun, percent error. I'm looking, but I'm not looking. Okay, here we are. So we have 1.2%. That's the percent error. And then EXP, MESTR, 577. So yeah, maybe I'm calculating this wrong. Either way, I do remember that it's a really high percent error. It's not like 1.2% like we have for the effective stiffness. But double check me on these calculations for the effective mass. Maybe I did something wrong and I didn't catch it. Okay, I'm going to put another poll to make sure that all of you typed all this out. If you haven't yet, that's okay. I'll give you a few minutes and then we're going to go over the plotting, which shouldn't be too long. You know, I never like to take the full time for the class because 3 hours is really long, but I know we're kind of getting up there now. Well, we're at like an hour and a half. All right, either all of you are fast typers too, or you just didn't type any of it. Okay, so one person's not done, so we'll wait a few more minutes.
I can type fast, but I still have to look at the keyboard.
Yeah. Yeah, sometimes I have to look down and the mic kind of obstructs my view a little. So it's kind of why I mess up even more. Did you guys learn typing like in elementary school? Like how to type correctly?
I type with exactly 4 fingers.
I heard like 5 of you talk at once. What?
No one talk.
I never type. I only type with 4 fingers.
Why?
It's how I learned.
Okay.
I hate it too.
Yeah. I remember in elementary school, like they had us as part of, I don't think it was like, I don't know. When we went to the computer lab, sometimes we would learn how to type and like on the home row, so how to do it correctly, but I still don't do it exactly like that. Okay, let's go on. All right, so now we're going to do our plots. Okay, so make another section here for plots. We'll start out with a lab view plot. So this is going to be the plot for the slope that we fitted for our data points. the least squared plot. Okay, so I'm going to type in figure 1. I'm typing in figure 1 because, yeah, I want multiple figures here opened up at the same time. So we'll assign this to figure 1. And let's see, did I do a plot before this? No, okay. So what I'm going to do here is a subplot. So if you remember subplots, that's basically just having multiple plots on one kind of graph or one figure, I should say. So we're going to have multiple plots and they'll be kind of side by side. So I'm going to do 1, 2, 1. And hold on, I want to look at my code to see. Okay, yeah. So we're actually, let's rename this comment, lab view and strobe gun. Okay, so we're gonna have a lab view and strobe gun plot. So we're gonna have one graph that shows our lab view plot and another graph that shows the strobe gun plot, but they're gonna be side by side on the same kind of saved figure that we have. Okay, so subplot 1, 2, 1. What I have right now is the first row. We're only gonna have one row, and then this is saying two columns. We have one row and two columns. And then this last argument, 1, means to put this figure that we're working on right now, or this plot that we're working on right now, in the first position. Okay, so we're going to plot m, that's our x-axis, m comma 1 divided by exp lvnf squared. So that's this plot right here. So we have m, and then we have 1 divided by the natural frequency squared. And we're doing that for lab view. Okay, and then I'm going to have bx, so this is going to be blue, and we're going to have x's, x kind of data markers. And I'm going to put, oops, I was confused why I just had a comma 2. So we have line width, and then a comma 2. So let's run this right now. And here's our plot. So we have a subplot here. So we have, we have one row, and then we have two columns. And this current plot that we have so far is in the first position. So these are the data points that we have. We have our mass going from 0 to 16 pounds. Of course, we converted the unit, so it looks different. And then we have 1 divided by the natural frequency squared right here. And we only had 5 data points, so you can see that right there. Now we also need to plot our line fit, our fitted line for our data. So for that, I'm going to do hold on, because I want to have another plot or another curve on that plot. So hold on, plot m m comma lv fit. So that's our lab view fitted plot that we found up here. Actually, did I not calculate that? Yeah, I didn't calculate that. All right, so we got to calculate this right now. So we're going to use Polyval. So right now, all we have is we used Polyfit. So that's that found our slope. But right now, all we have is we have the slope and we have our x data, but we need the corresponding y data as well. So for that, we're going to use the Polyval function. So I'm going to call this LV fit, just for our fitted line that we're going to have. We're going to use the Polyval function. So once I type that, it gives us some indications for what we can type. So Polyval p comma x, and you can also click on more help. I'm sure all of you know this, but so then this is going to evaluate a polynomial p. So in the first argument, we have to specify the polynomial. In this case, we're going to type in LV slope. Yep, and then we have to specify all of the corresponding x values that we have for that polynomial. And so in that case, it's going to be m, our added mass. So we're going to have Polyval LV slope. That's the polynomial that we have. And for that, we used Polyfit earlier on. And then we have comma m. So that's our added mass. So it's looking, again, at this polynomial LV slope. And it's looking at the corresponding x values that we have. And then it's going to give us, it's going to calculate corresponding y values for this polynomial. All right, so we had LV fit down here for plotting. And then we'll do a red dashed line on a line width of 2. And we'll do hold off. Spell line width correctly, that might help. And there we go. Here is our current plot right now. So the dashed line is the line that we got using Polyval. So it basically said, okay, we already made this, we found the slope earlier on using Polyfit. And then we are now making this, we're getting all the corresponding y value points by using Polyval for that polynomial. So then we can make this plot. All right. I know for me, when I think for last semester, when I was teaching 306B, I had to kind of review this stuff for myself. So maybe this is a bit of review for Polyval and Polyfit. Okay, now we need an X label and a Y label, and a legend would be helpful as well. X label, that's going to be our added mass. Yeah, I'm looking at my code. It's kind of wrong. I put pound force, but that's not the case because we have our units. They're different. What is it? Pound force times second divided by inches. Pound force times second squared divided by inches. I'll fix the formatting for this later on so it looks better. Y label. This is going to be inverse natural frequency of system. And that's rad, rad per second. Or sorry, second per rad. And those should be squared as well. Okay, so that's our X label, our Y label. And we'll add a title in here. Yeah, okay, so title will be lab view readings. I don't know. You can change the X label and the Y label and the title to something better. I'm just kind of thinking off the cuff here. So we're going to fix this formatting later on. So it's a fraction where we have the numerator on top, like on its own kind of line, and the denominator on the bottom. Okay, and now we need to add our second plot for our subplot. So before we do that, we have to also calculate or solve for the faded line for the strobe gun. So let's do that. We're going to do str fit equals polyval str slope comma m. Okay, there we go. Okay, so we're going to do that plot now. I'm going to have lab view there, and then I'll make a new comment. Strobe gun. So we're going to do subplot 1, 2, 2, because now we're in the first row, second column, and our position that we want to have is the second position. All right, plot m, comma, 1 divided by experimental strobe gun natural frequency squared. Okay, and then we'll do comma blue x's. Maybe you want to change this actually. I don't know. Line width of 2. Hold on. Plot m comma strobe gun fit comma. I think I used a red again. Yeah, again, maybe want to change that. Line width of 2. Hold off. X label. Added mass. Pound second per inch. Y label inverse. Don't ask why I'm typing it all out. Natural frequency of system second divided by rad squared. Title strobe gun. I don't think that's one word. Strobe gun. I guess I had it all capitalized. Readings. There we go. There's our plot. Cool. So another thing you might want to change, we have our y-axis. It's times 10 to the negative 4. You can kind of see that there. So you might want to change that. I'm trying to remember the exact code right now. We'll do AX equals GCA. That means get current axis. And then we're going to do AX dot X or Y axis dot exponent equals 0. Is that it? Wow, I remembered. So maybe you want to do this. I don't know, up to you. AX equals GCA. That should still work. Yep. Okay, so doing that code, that allows us to have just numbers, but I don't know, maybe that's too many decimals or numbers here. So up to you. Yeah. All right, any questions on the code so far? I think we have one more plot that we're going to make, and then that's it. Let me check the chat too.
Can you go back to the strobe fit?
Go back to what? To strobe fit?
Yeah.
Okay, that code?
Yeah. I didn't get it all.
Okay, there you go.
Okay, thank you.
Mm-hmm. All right, so yeah, I'm giving you guys basically all of the code, which you know, I'm fine with, but in future labs, I may have you do some on your own, just because you know this is important stuff to you to know how to do. But you know, so far we have the first two labs, and it's a lot of stuff. So I don't know. That's to be determined. I did that last semester a few times. I don't know. So maybe some of you in here, I don't know. You can either complain about it now, or you can say it was good. Right, so we have one more plot though. We have both plots overlaid. Is overlaid spelled like that or like this? I think it's like this, right? Anyone know?
Yeah, I think you have it right.
Okay. All right, so now we're going to overlay both of the plots that we had, that we just plotted, just so we can kind of compare the strobe gun and lab view a little more directly. So I put in a figure 2, so this will allow us to have both figure 1 and figure 2 outputted on the screen. So we're going to plot m, comma, 1 divided by m, comma, I think I put a period, 1 divided by exponent, or not exponent, experimental lab view, natural frequency, squared. Yeah, I really should just copy and paste. Line width of 2. We'll add in a comment. This is lab view. Hold on. Plot m, comma, 1 divided by experimental fit, comma, b dash dash. I want to. So right now I have blue x's. That's for our actual readings that we have. And I have a blue dash line for the curve fit that we made for lab view. Line width, comma, 2. Lab view slope fit or fitted curve. Okay, now we're going to add in another plot here. So m, comma, 1 divided by experimental strobe gun natural frequency squared, comma, gx. So we're going to have green x's now. And again, maybe you want to change some of this stuff. I just kind of somewhat arbitrarily assigned these colors and data markers. You might want to use like a green square or something to kind of differentiate it better. And this is our strobe gun. And then we have one more plot, plot m, comma, 1 divided by the strobe gun fit. Oops. M, comma. I typed some stuff wrong. I was kind of mindlessly typing this stuff in, so I messed up. That should be m comma lv fits. We're plotting that that fitted curve that we used for Polyval. 1 divided by experimental strobe gun. That looks right. Okay, and then plot m comma strobe gun fit. Strobe gun fit, and this will be a green dashed line. Line width 2. And this, choose strobe gun fitted curve. Strobe. Hold off. X label. Okay. Why am I? Yep, here we go. Just copy and paste it. X label, added mass, Y label, inverse natural frequency. And then we'll change the title. Maybe this one won't have a title. Let's just plot this right now, and then we can see what we have. All right, so this is our plot. So I need a legend, so we can differentiate what's what. So legend, we have lab view readings. Go away box. So that's the first plot that we plotted. That was the lab view readings that we had directly. So that's the natural frequency that we recorded directly using the lab view. And of course, our plot though is 1 divided by that natural frequency squared. Okay, and then we the second one is at the lab view fit. I'll say it again, you might want to have a better name than this because it's our fitted curve that we made using Polyval. Then we have strobe gun readings, and then we have strobe gun fit. Not a great name, so I would recommend changing that. And then I'll specify the location for our legend to be, what do I have? I put southeast. Okay, so southeast. And the legend box off. I don't want to see the box. Plot it. Actually, a box might be better in this case. All right, so there's that. And then I can also do AX equals GCA. So you see, I have AX equals GCA, and I also had that at 2 other points earlier on. So it's overriding that variable, but it's okay because MATLAB already processed and made these plots here. So I can use a different variable if I want, but I don't have to.
We only have 3 plots, and we have 4 legend readings.
Oh, did I not plot? I have 4 plots here. We have data markers in
Oh,
green.
no, yeah.
Yeah.
Okay.
All right, so I'll go back to the code so you can see it all. Okay. So that'll be the last plot that we have, and that'll be the end of the code. All right, so if you didn't type it all, then you should look back on this video, or if you were kind of confused on any parts, you should look back on it as well. Do you have any questions overall though? Plot it again. All right. Let's see. Anything else? Your first lab is due tonight by 11:59. So make sure to get that in. If you have any questions, put it in the Discord or stay after class. And this will be in 2 weeks, this lab report or memo. All right, so that's it for today. I know it took maybe a while, but I want to make sure you understand all the code and not just copy and paste it arbitrarily just so you can get the graphs. So if there's no questions, you guys are free to go, and I'll see you guys next week.
Thanks, Professor.
Yep.
Oh, I see what it was doing wrong. For me, I have to type location before I type like the location.
Oh, yeah.
Oh yeah, I couldn't see location on your screen. I see now. Okay, got it.
Do I want to take your fluid machinery exam, Kyle? I don't think that'd be a good idea anymore. Not even just because of the ethics, but because I would probably fail it now.
It's okay. I'm sure I'm about to fail it now anyway. So
I don't know. It's knowing you from the labs, I think you'd be okay.
Nobody fails Sharma's classes.
man, I hope so.